All right, so second. Exam 2 is on Wednesday. And the topics for that are everything up through um, uh, uh, pure tension and compression. And that includes pressure vessels. But no internal loads and no stresses due to internal loads. Okay, anybody have any questions about the test?
How many questions is it?
Let's see. I think it's 3 questions, but just a lot of, extra stuff for each question, Now, what's the stress if you rotate? What's the stress, like all that kind of stuff. So, but just 3 total questions. Any other questions about it? Okay. And then before we get back into new material, I'll go through number 9. The first thing we have to do, so this is just calculating internal loads. First thing we have to do is calculate the external loads. So I'll do a free body diagram of the whole thing. I'm going to assume that this pin can generate torques, but that roller cannot generate torques. There's some interpretation in there. It's open to a little bit of interpretation, but if you think of the way those joints work, that probably makes a fair amount of intuitive sense. So what do we have? So at the roller, or at the pin, I mean, we have a force, I'll call that RA. And then we have our distributed load. We have a torque over here of 4,000. We have a weight that's also a distributed load, but since we've already chosen to isolate this whole thing, I'm going to, for now, treat that as a point force. So that's a weight of 800 newtons. And we have a torque here. I'll call that fancy TA. And then we have a force here. I'll call that RB. That's a roller, so we know it's up. And then 10,000 newtons here. And I think that's everything. And then before we can do the calculations, we have to represent that triangular distributed load as a point force. We know that that has this length. So it's 1 meter long. So from the pin to the right end is 0.5 meter. So this is 0.5 meters. The height here is 15,000. The centroid is over here. And so 2/3 of 0.5 meters is 0.3 repeating meters. And then the total point force is the area, which is 0.5 times 15,000 divided by 2. So that is 3750, I think. And so I'll redraw this. We have 4,000 over here, a force of 800, a torque of TA, an unknown force vector RA, a downward force of 3750, a force to the right of 10,000, and an upward force of RB. And I think that's everything. Okay, so we have 1, 2, 3. Okay, so yeah, we can solve this. So Newton's second law. And I guess when I do my moments, I'm going to put my about point here. Remember, when I go to the cuts, I always put my about point at the left end point, but for the whole thing, I'm going to put it here. We only put it at the left end point all the time because it makes the algebra easier with the internal load variables. So Newton's second law, we have RAX, RAY plus 0, negative 800, plus 0, negative 3750, plus 10,000, 0, plus 0, positive RB is equal to zeros. And then the moment equation about the z-axis, the RA and the 800 don't produce a moment because that's our about point. The 3750, we have plus or minus a moment arm of 0.3 repeating times a force of 3750. About that red dot, that makes it rotate clockwise. So we want the negative. The 10,000 doesn't produce anything. It is 10,000, yeah. The RB does, and that has a moment arm of 0.5. And that would make it rotate counterclockwise, so we want the positive. So this is equal to 0. We get that RB is equal to 2,500. And then, let's see, RA, the vector, is negative 10,000 for the x component, and for the y component, I got positive, positive 2050. And then we still have to figure out that torque. So the moment equation about the x-axis, we have negative 4,000 plus TA is equal to 0. So TA is equal to positive 4,000. And that's Newton meters. Yep.
What was the torque in the middle of the body?
That is, so if there were no joints or anything, this 4,000 Newton meter torque would make it spin, right? It would make it have an angular acceleration. So you have to think about which of those joints keeps it from spinning. And since that pin joint has a pin all the way through, that's what prevents it from rotating like barrel roll. And so that's what that torque is.
There is always like a reaction torque to any torque that.
Yeah, in this class, since we don't have any angular accelerations, if you have an external torque, you always have to have a counteracting torque. That's right. Any other questions about the external loads?
What is our about point for the X for the rotation?
Okay, yeah, good question. Well, since these only appear as couples, it really doesn't matter. And that's why I never bring it up. Because remember, couples don't depend on the about point. So really, we could make the about point anywhere, and this math would look the same. Okay. But it would be, I guess it would be different if you had, so if you had a single, if you were creating a rotational, a rotational load by applying like a force to the top of this thing or something, then you'd have to think about, what your about point is and go through all those kind of calculations. I don't think I do that in any problems in this class. But okay, so now we have everything. So now we can figure out how many cuts we need. And let me draw this thing out carefully with all the things that we know now. So here is what's going on going into the start of the internal loads, going into the start of the cuts. So we have the 4,000 Newton meters there. We have I'm going to draw the distributed load for the weight like this. Because remember, weight is not a point force, it's a distributed load. So that is, this thing has a weight of 800 newtons. It's 1 meter long. So this uniform distributed load is 800 newtons per meter. Okay. Then we have our vector RA that is, I could write it as a force this way of 10,000, a force up of 2050, and a torque this way of 4,000. And then we have our triangular distributed load. That goes up to a maximum of 15,000. Then we have our point force here of 2,500. And our 10,000 here. So that is a complete picture of what we're dealing with going into the cuts. Anybody have any questions about this? All right, so how many cuts are we going to have to make?
Just two, I think.
Just two. So the question is, so you always have to do one no matter what. And so then you're looking for, are there any points in between the two endpoints where there are point forces, point couples, or changes in the distributed load function? Well, there are all three of those things. There's a point couple, a point force, and a change in the distributed load function. But they all happen at the same point. And so all we have is, we just have one additional cut. We have one cut where the right side is somewhere between these 2 points, and a second cut where the right end is somewhere between these 2 points.
But if one of these, it's not at the same point, then I have to do three cuts.
Then you have to do another one. Yeah, that's right. So what you're looking for, you're not looking for the things that, you're not looking for how many point forces, point couples, changes in distributed load function there are. You're looking for how many points there are where there's at least one of those things happening. Okay, so cut one is going to be for x values between 0 and 0.5. And so we have the 4,000 Newton meter couple. We have the distributed load from the weight. We haven't made it to all this stuff at the midpoint yet. So the only other things we have are the internal loads. So there's T, V, M, and fancy T. This distance is X. And now we have to, before we can do calculations, we have to represent that distributed load as a point force. So if I draw out that rectangle that represents that distributed load, I have a length of X and a height of 800. The centroid of a rectangle is right in the middle. And the area of a rectangle is the length times the height. So this is 800x. And so now I'll redraw this. So we still have the 4,000. We still have the internal loads. And then the distributed load is represented by a force down at the midpoint of 800 times x. And the distance is well, the distance of the whole piece that we've cut is x. That 800x acts at the midpoint, so this is going to be x over 2.
Why do we choose x instead of 0.5?
Because we need this free body diagram to represent every possible cut. Okay. So really, this represents infinitely many different cuts.
Okay.
Yeah.
But between 0 and 0.5, right?
Yes. So the X values could be, so like if you can think back in your notes, I've done things, I'm going to erase this in a second. You don't have to write this, but this represents a cut like that, and a cut like that, and a cut like that, and a cut like that, all the way up until just before we get to 0.5.
Okay.
Yeah. Okay, so now Newton's second law says 0, negative 800x plus t negative v is equal to zeros. None of the other loads in there show up because they're not forces, they're couples. And so t is equal to 0 and v is equal to negative 800x. And then I'll go to the moment equation about the z-axis. Question?
Where's the about point now, since we haven't gotten to that point in the beam? Is it going to be
Well, every time you draw a new free body diagram and do new equations, you can choose a new about point. So for the cuts, I'm just always going to choose an about point at the left end of our cut. So where I drew it there.
Free body diagram was in the middle, right?
Yeah, that's right. But there's nothing binding about that. You can move it for every calculation.
It'll walk back up to that.
So let's see. We have plus or minus. What's the moment arm for the 800x force?
Would be negative 800x, right? Because it's going clockwise.
Well, think what's the moment arm first of all?
0.5x.
0.5x, yep. And then the force is 800x. And now we'll think about which direction. Would this be clockwise or counterclockwise? Clockwise, yep. And then we'll go to, these always appear the same way. You add on the couple for the bending moment, and then minus v times x. You could think that through each time individually, but it always shows up the same way. It's a moment arm of x times a force of v, and then that's a clockwise moment. And so m is equal to vx plus 400x squared. And now I'll substitute in what we know v is. So m is equal to negative 800x squared plus 400x squared. And our final answer for m is negative 400x squared. And then we'll do the moment equation about the x-axis. The only couples about the x-axis are the negative 400 and the fancy t. Or that was 4,000, not 400, but negative 4,000 plus the internal torque, fancy t, is equal to 0. And so fancy t is equal to positive 4,000. And all of these are valid for x between 0 and 0.5. Okay, so now we're going to get to the horrendous one. This one wasn't really that bad, but the second half is going to get really bad, the second cut. What?
Now we're going to be including are they things?
It's not just the extra things. I mean, yeah, the main thing that's going to make it a pain is that we have to include that triangular distributed load. Okay, so our cut 2. This is for x between 0.5 and 1. And we still have the 4,000. We still have the distributed load representing the weight.
And why do you have to redraw that whole thing where I can put 800x down?
You could do that if you recognize that it's going to be the same, but I'm just trying to think through it sort of carefully, step by step. You're right that is how it's going to show up. So this is 800 newtons per meter. And then I'll say this is the midpoint, and we're going to have this R that's going to be negative 10,000, positive 2050. And then we're going to have the torque that torque is just 4,000, right? Yeah. So we have this point torque of 4,000. And then we have this triangular distributed load, but it doesn't go all the way up to whatever it was, 15,000 anymore, because, don't draw this, but I'm going to, so this triangular distributed load does something like that, right? And this value is 15,000. But the height of the part that we have depends on what our x is. So we have to come up with an equation for that line. And so I'm going to go back to the original one. This is our x equals 0. And we want an equation for the height of this line. And notice it, continues like this. This is the line that we're talking about. So it's going to have a negative y-intercept. And we have to think about the slope. Okay, so
Be under y equals mx plus b.
So it is going to be y equals mx plus b. M is going to be the rise over the run. So we can think of that as a rise. So if we think of starting at the pin joint, it rises 15,000 over a run of 0.5. So our M is equal to 15,000 over 0.5. So 30,000. And then you can maybe tell from the symmetry of this that if it rises 15,000 as you go from the pin to here, it must rise 15,000 as it goes from x equals 0 to the pin. So the y-intercept is equal to negative 15,000. So our y is equal to 30,000 x minus 15,000.
What did you do B again?
Well, I just recognized you can do any way you like to find the equation for that line, but I noticed that that it's half a meter from here to here. and half a meter from here to here. So if the change in height over this half meter is 15,000, the change in height over this half meter has to be 15,000. So that's how I did it. Okay, so we have the equation for that line now. I'll write that in here. So this is 30,000 x minus 15,000. And then we have the internal loads, T, V, M, and torque. And let's think about the distances.
You're not including the RT?
That's right. I'm not including that because the right end we're only considering up until right before you get to 1 meter. So this is the free body diagram that holds for everything right up until you get to those points, but not including the end points.
But the torque, the 4,000 on the left side.
We always include the left side.
Oh, the left side.
Yep, that's right. Okay, so this distance is x. This distance is 0.5. And now we have to think about, we have to represent those distributed loads as point forces. So let's do the part of the triangle first. Okay, what's the width of this triangle or the base of this triangle? At first you might think x, and usually it's x. Yeah. Yeah, so this one we have to go x minus 0.5 because it starts at 0.5. And the height is 30,000 x minus 15,000. And the centroid is 2/3 of the base. So that's 2/3 of the quantity x minus 0.5. And the area is this, the area is the base times the height divided by 2. Well, notice that I can write this as, so I can write this as 30,000 times the quantity x minus 0.5 squared, and then divide that by 2. So this is 15,000 times the quantity x minus 0.5 squared.
How did that minus 15,000?
Well, so the way I did this is 30,000 x minus 15,000 is 30,000 times the quantity x minus 0.5. So that's how I simplified it. Yeah. I'm just trying to look ahead to some of the algebra we're going to have to do, And then for the rectangular distributed load, that one has a width of x and a height of 800. And the centroid is right in the middle. So this distance is x over 2, and the area is 800x, which is the same as it was before, like you noticed before we started into this. Okay, so now I'm going to redraw all this. Redraw this free body diagram with those two distributed loads represented as point forces. We have the 4,000 Newton meter torque. Then at the midpoint of our cut, we have the downward force of 8,000 X. Then 2/3 of the way, nope, that's wrong. So let's put in first the point loads. So we have this force of negative 10,000, positive 2050. And then we have our torque of 4,000. And let me start writing out some of these distances. This distance is x over 2. This distance is 0.5. And now I'll draw the point force that represents that distributed load. It's 2/3 of the way from these point loads to the end. So that is like this. And the magnitude of that force is 15,000 times the quantity x minus 0.5 squared. And the distance from the left end to here, okay, well, we know that the distance from the point force to where that distributed load force acts is 2/3 times the quantity x minus 0.5. And now we want to add another 0.5 to that. So that is 2/3 x plus, I'm just trying to do this algebra in my head. So 2/3 x plus 1/3 of that, which is 0.16 repeating. So this distance is 0.6 repeating x plus 0.16 repeating. And then the distance to the right end is x. And then we have our internal loads, T, V, M, and fancy T. Any questions about those values?
You get the distance of 0.6x plus.
Okay, because we know that the distance from here to where that point force acts is 2/3 times the quantity x minus 0.5. But that's starting at 0.5 from the left end. So what that is, I'll erase this in a second. But that is 0.5 plus 2/3 times x minus 0.5. So that's 0.5 plus 2/3 x minus 0.3 repeating, which is 2/3 x plus 0.16 repeating. Okay. Newton's second law won't be too bad. It's the rotational Newton's second law about the z-axis that's going to be really a pain. Our about point is at the left, like always. So we have negative 10,000, positive 2050. And then we have that 15,000 times blah, blah, blah acting in the negative direction. So that's 0, negative 15,000 times the quantity x minus 0.5 squared. Then we have that downward 800x, so 0, negative 800x. And then the only other forces are T and negative V. So T is equal to positive 10,000. V is equal to negative 15,000 times the quantity x minus 0.5 squared minus 800x plus 2050. Any questions about that? And so now the terrible one, rotational Newton's second law about the z-axis with the about point at the left end. No x components of forces produce moments when you have just a horizontal beam like this. I guess the first one I'll deal with is the 800x. That has a moment arm of x over 2. And is that a clockwise or counterclockwise moment? Clockwise, so we want the negative. And then we get to the vertical part of this point force, the 2050. That has a moment arm of 0.5. Is that a clockwise or counterclockwise moment? Counter, yep. And then the one we've been waiting for this whole time, the moment arm of this ugly function is also an ugly function. So that is plus or minus a moment arm of 0.6 repeating times x plus 0.16 repeating times a force of 15,000 times the quantity x minus 0.5 squared. And is that a clockwise or counterclockwise moment? Clockwise, so we want negative. And then we have plus m minus vx is equal to 0. So we have to multiply this out. All right, well, let's do it. 15,000 times 0.6 repeating x plus 0.16 repeating times, if I multiply out that squared, x squared minus x plus 0.25. So that's 15,000 times 0.6 repeating x cubed minus 0.6 repeating x squared plus 0.16 repeating x plus 0.16 repeating x squared minus 0.16 repeating x plus 0.0416 repeating. And we can group this with this. And these two cancel each other. So we have 15,000 times the quantity, 0.6 repeating x cubed, plus that comes out to be negative 0.5 x squared plus 0.0416 repeating. And now I guess I'll multiply that out. So 2/3 of 15,000 is 10,000. So 10,000 x cubed minus 7,500 x squared plus 625. Okay, so
Is it the x squared is not the minus 0.44? Oh, just 0.5 is 0.44 on the x squared.
on the x squared, so we have negative 0.5 x squared times 15,000.
No, I mean before.
Okay.
You say the negative 0.6 plus the 0.16 should be negative 0.44. Not
0.5.
not 0.5.
Is that right? Oh, well, those have opposite signs. That's why. So
0.16 minus
you have like 0.66666 minus 0.16666.
because the negative is 0.6. I think my strategy was just to get rid of the repeat decimals by just multiplying them by being 1,000 because it's divisible by 3, so it kind of factors it out. It's more.
This seems right to me. Is that
I don't know. I did a
No,
different approach. My math is low.
I think you are right, because if you
Okay.
add all the decimals in your calculator,
Yeah.
just like plug a bunch in,
yeah?
they'll go to negative 0.999.
Okay.
Yeah.
Okay. Okay. So let's see what we have. So we have negative 400x squared plus, this is 1025 minus, so it's minus of all of this stuff we just figured out. So minus 10,000 x cubed plus 7,500 x squared minus 625.
Is it a plus? Or are you flipping it?
I'm flipping the signs because we have the negative from that being a clockwise moment. Plus m minus vx is equal to 0. And now we have to substitute in v. What?
Is it like Vx because it's Vx and Vy, or the X is like the distance?
We're multiplying by x because that is the moment produced by the force v with a moment arm of x.
Oh, okay, that's right. Thank you.
Yep. So m is equal to v times x. And then I'll go minus 10,000 x cubed. I'll group these x squareds together. So plus 7,100 x squared. And then plus 400. And v now is, good Lord. So v is this whole thing. So we have negative 15,000 times x times the quantity x squared minus,
So would it be minus 400 or no?
we have positive 1025 minus 625.
So when you move it to the other side,
Yep, you're right. Thank you. Okay, so
it's gonna be 100 and then 10,000.
yep, you're right. So everything should be flipped. So does that look right? Vx. Yes, I think that's good. Okay, so here is our v times x. We'll multiply that out. Plus 10,000 x cubed minus 7,100 x squared minus 400. And so m is equal to negative 15,000 x cubed minus 15,000 x squared plus 3750x plus 10,000 x cubed minus 7,100 x squared minus 400. So m is equal to 5,000x cubed. Those two, I think, should have. What?
Would it be negative 5,000?
Yep. So there. And then this would be negative 22,100 x squared plus 3750x minus 400. And if you take the derivative of this with respect to x, you need to get your v function back. And we do not. So something's wrong in there. I mean, there's just so many places you can make an algebra mistake, and I made all of them. Well, maybe that's not true, actually. It still could be right. What do you get when you multiply this all out? So negative 15,000 x squared this should have been, this I did do wrong. This should have been minus x plus 0.25. So this is plus. And this is minus. So 15,000 minus 7,100. This should be plus 7,900x squared. Minus 3,750. Okay. So up here, multiply this out. Minus 15,000x squared. Plus 15,000x. And then minus 3,750 minus 800x plus 2050. Okay, so that's negative 15,000 x squared. Plus 14,200x minus 1,700. The leading term is right. 7,900 times 2 is 15. That's wrong. And that's wrong. So 1/3 of our answers make sense. Anyways, 100%, I can tell you that is how you do it. There's just algebra mistakes in there. Okay.
Test, would you want us to fully simplify it down, or could we just include the function?
Well, you know, on a test, I would never give you something like this. Want to see a way that makes more sense in a problem like this to do it? That I haven't really told you this way because you don't see problems like this. But remember, we have these relationships that say negative dv dx is equal to q, and dm dx is equal to v. Okay. So we can just go straight from our q function and integrate up and then just use boundary conditions. So let's see. For our second cut here, so integrating those and then matching boundary conditions. Makes more sense here. Okay, so so first we have to find our q function. We have so we have the sum of two functions. You know, we can think of this as the q for the weight plus the q for the triangular distributed load. The weight is just 800. That's a constant, you know, uniform distributed load. The triangular distributed load we came up with
It's down. I think you passed it. The 15,000 times X model.
so it's just this one. We just need the height of the distributed load at each x value. So 30,000 x minus 15,000. And so q of x altogether is 30,000 x minus 14,200. Now v is going to be using this relationship, the first one of these. V is going to be negative integral of q, which is negative 15,000 x squared plus 14,200 x plus c1. And then m is equal to the integral of v dx And so that is negative 5,000 x cubed plus 7,100 x squared plus C1x plus C2. And now you have to figure out what the values are, like right at these, like you have to figure out some boundary conditions you can use. One thing you could use here, this is only for the second cut, but we could figure out that so I'd have to think about this for a second. So at x equals 0.5, the shear force is, so from the first cut, it was negative 400. And then we went up 2050. So V is equal to 1650. And then at x equals 0.5, our bending moment is so it was negative 100. We didn't have a point couple about the z-axis, so the bending moment is going to stay negative 100. And you can use those to find the C1 and C2. But you can see that this way of going is way, way faster in this case. Still, I'm sorry I gave you this problem. I guess I'd forgotten I gave you a problem that took this much work. But I'd say overall, just go through the algebra. Don't do the integration thing. But that's just an example of, you can see sort of how the integration idea would work. And in very complicated cases, it can sometimes save you some time. But anybody have any more questions about that?
I think the problem with reverse substituting is when we plug B in, we didn't put it complete, just a part. So B.
Oh, we didn't put these in.
Yeah, those.
Okay. Yep, you're totally right. That's totally right. But we're not doing it again.
Yeah. No.
There ain't going to be no rematch. Okay. Let's stop there.
But do you
That's-
ever have to use it asks like the cross section with the height and the width? Do you ever use that?
No, that's in that problem because I noticed that as I read it, because it used to be a problem that asked you to calculate stresses.
Okay.
And that's what we'll use it for. But I took that part out to make it an internal loads problem. But that's the stuff that we're getting to now. Okay. Test on Wednesday. Not on this.